all of you have taken electronics course before?
Yes.
Okay, it's compulsory,
Yes,
right?
Doctor.
Yes, Doctor.
So in the electronic course, you already learn on the digital circuit, such as the, right, in the digital part of the electronic. So in the electronic course, you learn about analog circuit and also on the digital circuit. Okay, so for the microprocessor, so you know what is a microprocessor? So microprocessor is your CPU, all right? It's your CPU that is located inside your PC, so that controls everything, okay? So it controls every function, so it is like a heart of the computer. Okay, so microprocessor is heart of computer. So without that, you cannot call it as a computer because that is missing. Okay, so it's like a human. So if there's no heart, then you will call it a human. All right. Okay. All right. So okay, only 2 students are missing. So let's start with the introduction to the course. Okay. Okay, so you can see the presentation.
Yes, Doctor.
Yes.
All right. So this is a 4,000
Yes,
course.
Doctor.
Okay, good. Okay, thank you. So basically this is 4,000 level course. So basically it is the 3rd year or 4th year level course. So basically it has a prerequisite of you need to take the electronics course before taking. Okay, let me get your friend in. Okay, so the title of the course is about the microprocessor and the micro. So the as I said, the microprocessor is the CPU, or which is the heart of the computer. All right. So it is important for you to program this microprocessor in order for you to do the function that you like. For example, you want to turn on your camera. So it is actually there is an instruction sent to the microprocessor, okay, to turn on the camera. Okay, so without that function, then you cannot turn on your camera, even though it is connected. I mean, the hardware is connected to the circuit, but in terms of function, it won't function because the function need to turn on, turn off, or even change the background and so on. It is related to the software. Okay, so you need to have that software to construct, okay, to construct or giving instruction to the microprocessor, okay, to uh, in order to work, okay. So for example, you need to turn on the camera, so you need to send the instruction to the camera to turn on, okay, and then it is working. All right. So I bet many of you have known me. So this is my background. So I was a graduate from the Purdue University in the United States. So my background of study was electrical engineering, and I did the Master of Science in sensors and insertion in UPM, and I have a PhD in also electronic engineering, specifically in wireless communication, and my expertise in the MATLAB and algorithms. Okay, so you can go to my profile page. It's there, and you can contact me by either by email or mobile. All right. So, but physically, we still cannot meet yet. Okay. Right. So hopefully we can meet soon. All right. So when we are allowed to enter UPM. Okay. So about the course. So general information. So the course is 3 credit hours. So we have no lab, but we still need to assess you on the psychomotor skill. All right. Because this course requires you to do the coding. All right. To do the coding and also the mini project. Okay, so we're going to meet every Tuesday and Thursday. Okay, so the time is now, and also on Thursday will be at 4 p.m. Okay, am I correct with the time? Okay, so all right, so it is compulsory for all of you to attend all lectures. Okay, so let's go to the course synopsis. So this course is basically going to discuss about the computer and microprocessor architecture. Okay, so microcomputer hardware such as the microprocessor. So inside the microcomputer, we have the microprocessor, memory, and peripheral devices. Okay, so peripheral devices such as your keyboard, mouse, okay, so your monitor. All right, so that's all the peripheral devices. Okay, and then the information that that actually to run your computer is stored in the memory, or you call it as sometimes you can call it as ROM or random. um, I'm not sure what's the term, and then O term is, and then M is for memory. Okay, but for RAM is already is a card that is installed on the computer. So that's additional RAM will have the ROM. But the ROM is the one that is already inside the motherboard. All right. So that is attached to the computer, to the microcomputer. So there are certain functions that need to be there in order for you to turn on the computer. All right. So that's basically the function of ROM. But for the RAM is the one that is used to run the application software. Okay, so such as your Windows. So your Windows can be installed. The all set of instruction can be put on the RAM. But for the ROM, you need to the ROM is essential for you to store the function to construct the microprocessor to do its function. Okay, and then for coding the microprocessor, we need to have the software emulation. Okay, where there is an emulator. So the emulator name is 8086. Okay, 8086. So you can find that and then you can download it. Where we will use the assembly language. All right, the assembly language to create the coding in order for you to communicate with the microprocessor. Okay, and then lastly, as I said, so you need to carry out a mini project to complete this course. Okay, so this is what will be accessed from you. Okay, so the first one is on the knowledge. All right, of course, the CTPS, critical thinking and problem solving skill, and lifelong learning. All right, and then the next one, the communication skill. So this one is accessed during the presentation. Okay, and the last one it will be on the psychomotor, all right, where you need to construct the programming using the assembly language. Okay, so this is the plan of learning. So within this week, we will discuss about the binary number. So we will revise that, and then maybe the extended version of what you learned about the binary number, and also the logic operation. And then we are going to compare between the binary number in the week 2 with the logic operation. And then in the week 3, we're going to look at the architecture of the microcomputer and the microprocessor. Okay, and then we're going to look into the microprocessor hardware. Okay, before we having the test 1. And then once we finish with the test 1, then we're going to look into the assembly language. Okay, so the assembly language is the one that we use to communicate with the microprocessor in order to make the microprocessor doing its function. Okay, so basically on week 6, 7, and 8 and 9, so all involves 9 and 10. All right, so all involve on the assembly language. Okay, until week 12. Okay, and then the last 2 weeks we will make comparison on the microprocessors. So there are many types of microprocessors, so that you will study later. Okay, so for the textbook, okay, so you can find these 2 books. So these 2 books are the one that I'll be using the teaching material from this book to teach this course. So it is highly recommended for you to get this book to study further on the microprocessor and a microcomputer. Okay, and also the assignments will also be taken from this book as well. Okay, so this is what are you waiting for. So this is about how the marks are distributed for this course. So for the assignment, okay, it will be, the mark there should be 10. Okay, let me fix that. Okay, so assignment will be 10%. So in terms of the assembly programming, there will be a couple of quizzes throughout the course. So that will contribute about 10% of the marks. Okay, so we also have the mini project with presentation, which is also 10%, and then test 1 will be 15%, test 2 will also be 15%. Okay, and then the final exam, as usual, will be 40%. Okay, so the total marks is 100. Okay, so all are clear?
Clear.
Okay, thank you. All right, so happy learning. If you don't know, please ask. So the human should learn better than the machine. Okay? All right. Okay, I will share these slides later to the WhatsApp group, and then I will also update the Putra Plus later within this week.
Doctor,
Yes,
do you have a PDF of the book?
I don't have it right now. If you want, you can just find it. I think it's available on the internet. Okay. Actually, I only have the teaching material of that. I don't have the PDF copy of the book, because I'm going to get the one on the physical book, all right? Because I already requested it from the publisher. Okay, but I think it is available on the online, so you can just find it. Okay. All right. Okay, so we finished with the introduction of the course. So let's get started. Give me 1 minute to check on the slide. Okay. All right. So we're going to
Dilaki pun.
uh, I think one of you haven't turned off your mic, so there was a background sound. Okay. Okay. So first of all, we're going to look into the computer history before we start with the binary numbers and also the logic gate. So you will get a big overview on how the computer evolves. Okay. All right. So okay. So long time ago. So you have a computers. Okay. So this is actually is a very huge. As you can see from the picture, you have so the weight of that is 250 tons, so which is very heavy, and then it houses more than 200,000 vacuum tubes, okay, which is utilizing power of 3 million watts. So this vacuum tube computer was the first computer ever built, all right. So first ever computer ever built in the history. So the dimension for that is actually it's like the factory. Okay, so it is 10,170 meter square area is taken up to build the factory of the computer. All right, so that's the first computer ever built. As you can see that in the bottom that you have that's the vacuum tube, right? That's the vacuum tube that was functioning, right? That was functioning to um, to help uh, to help with the building of the computer, right? So this basically this vacuum tube, if you can find out, it was actually in your old set of television. Maybe it wasn't during your generation. Maybe you haven't managed to found that TV anymore. Okay, so in the second generation, starting from 1956, so the people managed to make a smaller computer, but it is still big. Okay, it is still big because the computer needs to take half of a room. Okay, the capacity at half of a room for the computer. So for example, we have here the Harwell Decathlon computer. So under restoration at the British National Museum of Computing. Okay, so if you are able to go to the UK, all right, so you can go to this museum, okay, to learn about, to see this is the second generation computer ever built, okay, in this world, okay, and then the third generation. So that is the started the era of the IBM. Okay, so the IBM 360. So this one is made by the IC. Okay, so once the IC are found, so the computer are able to be built using the IC. So IC is the integrated circuit. Okay, but during that time, the microprocessor still haven't been invented yet. Okay, so it is still based on the integrated circuit. So the first version based on the vacuum tube, and the first and second based on the vacuum tube, and then for the third generation is based on the IC. Okay, and then the first microprocessor and microcontroller was found. So these are the examples of the first microprocessor and microcontrollers ever developed. All right. So we have from the Texas Instrument, which is TMS 1000 model. Okay. So Intel also developed 4004 model, the microprocessor, and from the Motorola also built the 16800 version of the microprocessor. Okay, so you can see that it is like your microchip right now where you use. Okay, so that's the first ever version of the microprocessor. Okay, so you have the generation evolved. So first from the vacuum through the vacuum tubes, and then the half room computer was built by the from the transistor. Okay, and the third generation is made from the IC, and then up to now it is based on the microprocessor or micro computing unit. Okay, so that's how the evolution of the microprocessor. Okay, so we also have right now, nowadays we also have the microcontrollers. So microcontrollers is like the one that you found, okay, the one that you found in the Arduino board. If you ever heard about the Arduino, so for the general purpose microprocessor, so we have CPU, RAM, ROM, I/O port, timer and serial port, and we have the buses. But the difference with the microcontrollers, all of these have the input and output at the I mean near to the what we call that the microprocessor inside the microcontroller. Okay, so that's basically the difference between the microprocessor and microcontroller. All right. Okay. So for the microcontroller, so these are the names. I bet you are, you know, I mean, commonly, because it's commonly used nowadays. So we have the 8-bit microcontrollers, which is from AVR, PIC, HCS128051. Okay, and we also have 32-bit microcontrollers, which is the ARM processor. Okay, The ARM processor is used in the today's mobile phone, all right? And we have the AVR32, PIC32, Codefire, and PowerPC. So these are the common microcontrollers used today. All right, so we have the architecture of the AVR. Okay, so one type of the microcontroller. So we have the CPU. So CPU is the microprocessor. So we have the program ROM where we need to store as I said, we need to store some function in order to construct for the CPU to do the function. All right, so these are connected, the CPU are connected by the buses. So by buses, it's going to the RAM, EEPROM, timers, other peripherals, ports, and interrupt unit. Okay, so buses is like a highway, all right? So buses is like a highway. So highway from CPU to the other part of the computer. Okay. All right. So this is like the microcontroller that you found on the Arduino chip. So this one is found on the Arduino Mega 328. Okay. So basically you have the inputs and output pins. Okay. The internal, the power out voltage. All right. And the digital input and also the digital output. Okay, so the classic version of the AVR microcontroller. So you have 80 90S2313, right? For the 80 mega, all right? So this one is used on the Arduino Mega. You also have the tiny, okay, the 80 tiny, and the special purpose AVR. Okay, so the model is 80 and the X Mega. So it features, it gives you the new features like dynamic memory access, DMA, DAC, crypto engine, and so on. Okay, so yes, you have any question?
What is AVR stand for?
AVR is the name of the chip. I'm not sure about the abbreviation. Okay, you can check. Is this like the what we call ARM? Okay, it is like the ARM. So ARM. So AVR. There is actually the AVR is actually the company, okay, the company that developed the microcontroller. So they name it as the AVR. Okay, because I checked on the Wikipedia, so it mentioned that the creators of the AVR give no definitive answer to what the term AVR stands for. Okay, but the people giving the AVR as the Alf and Vigas RISC processor. So basically, the names of the founder. All right, the name of the founder. So the founder of the AVR microprocessor was actually the two students from Norway. All right, they are from the Norwegian Institute of Technology. The names are Alf Egil Bogen and Vigard Bollen. So I think that's so it took A and B for the name of the microprocessor, and R is RISC. Okay, so you can look at the Wikipedia, okay, to study on the names. All right, so you can just Google A and you will find the answer. Okay, but the creators didn't give the definitive answer to ABR. So actually, it is not acronym. Okay. All right. So these are some members of the classic microcontroller. So we have 8090 version of the microcontroller, and the data RAM is only 128. Right. So this is just some properties of that ROM. Oh, sorry, of that micro controller. Okay. So this is for the Mega family. So for the Mega family, so we have the 80 Mega, and then we have up to 128K of ROM for the 80 Mega 1280. Okay, so this is some examples of the 80 Mega chips. Okay. Alright, so we also have so this one is the chip. All right, this one is the chip. Okay, so you have magnetic. So this one is the rectangular version, and then another one is the square version of the microcontroller. So you can see the layout of the pins. All right, so we are making this design because first, to make a compact, to decrease the size of the microcontroller, and also to have as many function as possible to the microcontroller. Okay, so the main aim, if you are designing the microprocessor or microcontroller, of course you want to decrease the space because you want to make it smaller and smaller. So why? Because make the your microprocessor smaller, of course you could add more function to that. Okay, so like today's computer, the CPU is very small. Okay, when it is very small, of course then you can add more function. Okay, without having much space. So you can have a big as nowadays you don't even need to have a separate CPU from your PC. It can be attached to at the back of the monitor. Okay, for example, when you are having a small microprocessor. Okay, so that's the evolution of the technology. Okay, so this is the difference of the chip. Okay, so the on the left is the chip is called SOP, and on the right side it is SOIC. Okay, and this is the CBGA. So you can see that the difference between those chips and the names. Okay, so that one was related to 80 mega, and then this one for the 80 tiny. So as you can see, the ROM is very tiny. So it is from 1K to 8K only. All right. So for the special purpose, all right. So we have the code ROM of 128 and 16 K as well. So the special capabilities is for, let's say, for 8090U USB 1287. So we have the USB host, all right, which can control the USB host, and then 80 mega 169, which controls the LCD. Okay. For another one, so we have it controls the advanced pass width modulation. Okay. All right. So this is for the X mega AVR. So we have a couple of flash ROM. All right. So different variety of the ROM depends on the number of the chip. Okay. All right. So So you must be familiar with Atmel, alright? So Atmel is the name of the chip. Group is called Mega, and then 128 usually defines the ROM, alright? Which is the flash. So 128 we have 128 K, and for the 8090S, right? The classic group, right? So 80 Atmel, and for 433, so the flash is 4K. So which is a very big ROM. Okay, so for further references, you can check this. I will share this later today. All right. Okay, so any questions so far? Okay, next we will continue with the binary numbers and also the logic gates. So as I mentioned in the learning plan, so for the first week, you're gonna solve binary number and the logic operation. Okay. All right. So let's get started with the binary numbers. By the way, give me 2 minutes. All right. Okay. So, all right. So for the binary numbers, as I said, you can refer to the book of the X86 PC. So basically in this course, you're going to learn on how to code. How to code to give instruction to the microprocessor. So basically, it's very low level programming. Okay. So it's like you are learning about how to make your computer works. Okay. So you have the controller, microprocessor, and then you are instructing the microprocessor to do the, okay. So it's like you are designing a computer, right? So okay, so in this chapter, so we're going to learn about conversion of any number from base 2, base 10, or base 16 to any of the other two bases, add and subtract hex numbers, add binary numbers, represent any binary numbers in 2's complement, okay, represent an alphanumeric string in ASCII code, describe logical operation. Okay, so you are familiar with this: AND or not, XOR, NAND or NOR. Okay, and then use logic gates to diagram simple circuit. Okay, so basically the learning outcome, you should be able to explain the difference between a bit, a nibble, a byte, and a word. Okay, and you also should be able to give precise mathematical definition, okay, in the terms of kilobyte, megabyte, gigabyte, and terabyte. And you should be able to explain the difference between RAM and ROM, okay, and describe their usage, and then describe the purpose of the major components of a computer system, okay, and list the three type of buses. As I said, the bus is like a highway, okay, in a computer system, and describe the purpose of each bus. Okay, so all right. So next, we need to describe the role of CPU in computer system, and this is a major component of the CPU, and describe the purpose of that. Okay, so you need to know how it begins, right? So about the number-based system. So why do we have the 10-based system? Okay, so in fact, it is a common. So we have 10 fingers, so that's why we have base 10 system, right? So that's why we first started with number 1 up to number 10. Okay, so that's how we learn since we are baby. All right, so that's why the human starts with the base 10 system. Okay, so human use base 10. So the base 10 is called a decimal. Okay, so decimal number, okay, so base 10 arithmetic, and the computers use the base 2. So base 2 is just two numbers, is 0 and 1. Okay, so for the base 10, there are 10 distinct symbols. So it's from 0 to 9. Okay, remember that. So it's 0 from 9. It's not 1 to 10. So the base 10 is from 0 to 9. So why? Why is from 0 to 9? Because when 10, it involves two-digit numbers. So that's why we use 0 to 9, because all of that are the single digit number. So that's the reason the base 10 number are from base 10 number is from 0 to 9. And for the base 2, so we use the binary digits. So binary digits are 0 and 1. And then these are referred as, okay, these are referred as bits. The binary system used in a computer because it represents the two voltage. Okay, so why we use only 0 and 1? Because so it is simple, it's like a switch, right? It's like a switch. Switch on and switch off, switch on and switch off. So it's just two functions. So that's actually the function of the transistor. So turn on, and turn off. Okay. Okay. All right. To convert decimal to binary, okay, we divide the decimal number by 2 repeatedly until its quotient is 0. Okay. I bet you already learned this in the electronics, right? Okay. How to do the conversion. So this is like a revision. Do you guys still remember how to do the conversion?
Slightly.
Slightly, right? So we have example here. So convert 25, for example, 25 base 10 to the binary. Okay, so we divide 25 because binary is base 2, right? So we divide base with 2. So we divide 25 with 2. So we get 12. All right, so we have remainder of 1, right? So that's 24, and then we have remainder of 1. So we use that number, all right? So it starts from the least significant bit, okay? 12 and 1, okay? And then you use 12 and then divide with 2. So you got 6, but you don't have any remainder, so that's a 0. And then you use 6. Okay, so now you use 6, bring over there, okay? 6 divided with 2, so you get 3. And then 3 divided with 2, you get 1. But you have reminder here, okay? So you put the reminder there, and then you use 1. 1 divided with 2, so because it cannot be 1, right? So it's 0, and then you have the remainder of 1. So how to write in the binary? So you take from here, from the most significant bit, from the bottom one to up, right? To upwards. Okay, so you taking to that. Okay, so it will be 11001. Okay, base 2. So that's how you do the conversion from the decimal to the binary. Okay, how about to reverse that? Okay, to convert from the binary to decimal, it is important to understand the concept of weight associated with the each digit position. Okay, so each digit position of a number in base 2 has a weight associated with that. Okay, so let's say you look here. Okay, so we look at the number, the same number as we use from the example from the previous example, this one. Okay, so you take the least significant bit, all right, the least significant bit, this one, okay, put it there, 1, and follow to that direction. Okay, it will be 1 0 1 0 1 1, and then each of these have the weight, right? So this is 2 to the power 0, okay, and then this one 2 to the power 1, and 2 to 2, 2 to 3, 2 to 4, and 2 to 5. Okay, all right, so you multiply that, right? So 2 to 0 is 1, right? So 1 times 1, we got 1. 2 to 1 is 2, times 0 is 0. 2 to 2, 4 times 1 is 4. 2 to 3 is 8, times 0 is 0. 2 to 4, it is 16. So times 1, so you got 16. And 2 to 5 times 1, 2 to 5 is 32, times 1 is 32. So you sum up all of that, okay? So sum up all of these, so you obtain the decimal number, all right? So you obtain the decimal number. Okay? So this is the equivalent base 10 to this base 2. Okay, to that base 2. All right. Okay, so you're clear with that? So
Yes.
this is just Yes, any question?
No.
Okay, no question. Okay, good. So now it is just a representation of this base 10 number. All right. So to convert that to the weight, all right. So it's like the weight of the base 10. So you convert that to also to decimal number. So for example, 3 is 10 to 0, 8 is 10 to 1, 6 is 10 to 2, 0 is 10 to 3, and then 4 is 10 to 4, and 7 is 10 to 5. Okay. So when you multiply that with the weight, okay, this number back to the weight, so you obtain that, you sum up, you also get the similar answer. Okay. So that's the way on how to do conversion from the binary to decimal. Okay. So binary to decimal, you use the concept of weight. Okay. But for decimal to binary, you use the concept of division of that base number. Okay, so you need to be able to distinguish that two. Okay. All right. Okay, so it might be easier. You can do in terms of this table as well. Okay, for example, you know already the weight. Okay, so because you know that, okay, this one is for 2 to 0, so it is 1, right? So here it is 2, 4, 8, 16, okay, and 32, 64, and so on. All right. So you put the weights, okay. So you put 1, 2, 4, 8, 16, and then you put the digits at the bottom there, and then you just multiply those, 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 and those. Okay. So you sum up all of that. Okay, 16 plus 8 plus 0 plus 0 plus 1. So you obtain 25. So 25 base 10. So it is a much easier solution. Okay. All right. So, okay, you also can use the concept of table as well by using the weight. Okay. So now you want to from decimal to the binary. So how to do that? Okay. So for example, okay. So the weight, so because of the, you look at the number first. So it is 39. Okay, it is 39. So you assume that, you know, the binary can be, okay, what is the binary number, binary value between within this 39? It is 32 and 64, right? It is between that. Okay, it is between that. So you take on the smaller side. Okay, so you take on the smaller side. So you put only up to 32 as you list here. So you start from 2 to 0, 2 to 1, 2 to 2, 2 to 3, 2 to 4, 2 to 5. Okay. So that's equals to 1, 4, 8, 16, 32. Okay. And then, so you need to find out, the total of this, right? The total of this should only be 39. Okay. As it should be only 39. So the on the second row, you are only able to write either 1 or 0. So you can play with that. Okay, first you put add 32, right? So it's already 32. But if you add 1 here, so it will be more than 39 because your aim is 39. Okay, what's next? Okay, if okay, it's already 40, so it's more than 39. So you still put 0 there. So is it possible for you to have 4? Yes, it is possible. So 32 with 4, so you have 36. So now 3 left. Okay, 3 left. And then is able for you to add 2? Yes, it is okay. So you can add 2, so you got 38. And then the last one, you add 1. So you sum all of this, it should be 39. So you get the concept? Equation so far? So for this kind of solution, this one is like a guessing. So it's not direct, it's like a guessing to convert decimal to binary. But for the binary to decimal, it is direct. Okay, like this one. Okay, like this one, it is direct. So you just put the weight and then you put this number to the second row. Okay, to the second row, and then just do the multiplication. But for this one, for the decimal to binary, you need to do the guessing. Okay. Any question?
No.
No.
All right. So, okay. Now we move to higher numbering coding system, which is the hexadecimal. Okay. So for the hexadecimal, so we have the base 16. So base 16 is called as the hexadecimal system. So it is a convenient representation of binary numbers using the 16 digit. Okay. So for the first 10 digit from 0 to 9, so it is similar to decimal system. Okay, base 10. For the remaining 6 digit, we use the letter A, B, C, D, E, and F. Okay, so you need to remember that. So it is not we use from 0 to 15. So we use from 0 to 9 and A to F. Okay, so that's the hexadecimal system. 0 to 9 and A to F. So you have total digits of 16. Okay, so it is easier for humans to express string of 0 and 1 like 100, 100, 10110 as the hexadecimal number, right? 896H. So it is easier to use that, right? So rather than you are using the 10, the binary, because binary will be a very long number. Okay, so hexadecimal can make the binary system, binary number shorter. Okay, you look at the table on the right side. So we have the base number system. Okay, so for the decimal, we have from 0 to 15. Okay, because it's base 10, so it is normal. So but the base 10, so we have the decimal from 0 to 15, for example, and the binary. So we have up to, okay, from 000 up to 1111. So this one, 220, 221, 222, 223. Okay, is equal to 15? Yes, 223 is 8, 4, 2, 1. 8, 8, 4, 2, 1. So the total is 15. So for hexadecimal, so it's from 0 to 9 and A to F. So that's cover the 16 digit numbers. Okay, to represent a binary number as its equivalent hexadecimal number, start from the right and group 4 bits at a time. Okay, so you need to group 4 bits at a time. So this is 1 bit, 2 bit, 3 bit, and 4 bit. Okay, so you group that. Okay, so another 4, you group that. So that's grouping 4 bit number at a time. And then what you need to do is replace each 4 bit binary number with its hex shown. Okay, all right. So how to do the replacement? So you have this. So you need to, okay, you need to first knowing what is this number represent. Okay, so this is 221, 220, sorry, 220, 221, 222, 223. Okay, so this is 1, okay, 1 value, and then this 222. So the sum of all of that is 5. So you get 5, and then 111. So the total is 15. Okay, so in the hex it is F. Okay, as this one. So when it is 15, then it is F. So you put F. Okay, so for 1001, so this is 220, 221, 222, 223. So 223 and 220, so it is 9. 8 plus 1, so it's 9. Okay, so therefore, in the hex number, so this number is 9F5. Okay, so or you can write 9F5 base 16. Okay, that's your hex number. All right, so to convert from hex to binary, okay, so now you have hex. Before this, you have binary to hex, and then now hex to binary. Each hex digit is replaced with its 4-bit binary equivalent. Okay, so like before, we expand to 4 bits. Okay, before this we group 4 bits, but now we expand 4 bit. For example, 29B. So we have 29B. So you expand all of that. Expand to 4. Okay. So what is 2? It is 0010 91001. Okay, B. So what is B? B is, as you remember, so we have 9, 10, 11. So B should be 11. Right? So we have 2 to 3, which is 8, 2 to 2, which 2 to 1, which is 2, and 1. So 8 plus 2 plus 1, it is 11. So you got B. All right. So you just take the significant figures. Okay. So the zeros in front of that won't be used. So just take from 10, 1001, 1011, base 2. Okay. You got that? All right. Any questions so far?
No, doctor.
Okay. Okay, so
Doctor,
yes.
the question before,
Mm-hmm.
uh, why the answer is 10 and then the upper is 00?
As I said, these two, because this 00 is not significant figures, so it's not meaningful. All right, so that's why you just take 1. If the 0 at the back, on the right side, okay, then it is important, so you must put. But if it is on your left side, okay, let's say at number 2 here, 0 in the front, so you can just neglect that 00. You can also write 00, 10, 1001, 1011, but it is similar like this one, right? The value is similar. So why not you just write this? Okay. If you calculate back, it is similar 0010, 1001, 1011. It is similar to this one. Okay, so that's why we just make it simple. So just neglect the first two zeros. So the zeros, the zeros at the left side, at the most left, okay, can be neglected. Okay, so that should answer your question. Okay, you clear?
Clear, Doctor.
All right. Okay, so we want to convert directly from decimal to hex. Okay, so now, so we already settled with binary to hex, hex to binary, and now decimal to hex, base 10 to base 16. Okay, we want to convert directly from decimal to hex by repeated division, keeping track of the remainders. So we use the concept of remainders like we do to convert from decimal to binary. Okay. All right. So we have, for example, we have A 6B2. Yes, you have question? No question. All right. So we have 6B2. Okay. First, we can convert that. All right. So we can convert that.
Cakap Melayu.
Any question? All right. Okay, so we convert 6B2 to first to the binary. Okay, so to binary, as before, we need to expand. Okay, expand this to 4, this to 4, and then this to 4 group. Okay, so for 2 is 0010, and for B, it is 1011, and for 6, it is 0110. Okay, so as I said, you can neglect this 0. Okay, because it is at the most left. Okay, so this is what you have. 110 1011 0010. So 110 1011 0010. Okay, and then started from the least significant bit from here. This is, so you convert to base 10. Okay, so 1 2 4 8 60 32 64 128 to 56 512 1024, and then you sum all of that. All right, so sum all of that, which one have the 1? Okay, so for 0, of course it will be 0. Okay, so of course it will be 0, so you just add this, that, 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 and that, and that. Okay, so this is how you do that. So the answer will be 1714. All right, look at B. So now you have 4 bits. Okay, you have 4 bits of the hex. So of course, when you expand this, you have 16 bit of the base 2. So this is for 9, F, 2, and D. All right. So it is represented by that for the base 2. Okay, now of course it will be very, very large. Right. So here there is no term to be neglected because the head is 1. Okay, so you need to take all. Right. So all of this should be 16. Okay, so started from the least significant bit from here. So you start 1, 2, 4, 8, 16, 32, 64, up to 32, 7, 6, 8. Okay, so this is 2 to the 16. Okay, 2 to the 16. All right. Okay, so 2 to the 16. sorry, it's 2 to the 15, all right? Because you start here is 2 to 0, okay? 2 to 0. So it's 2 to 15. It's 2 to 15, so you got 32,768. If you calculate that by using calculator, you get 32,768. Okay? So as before, you take only the one that have one bit. Okay? One, okay, this one, that, and that, and that one, and that one. So you sum all of that. So the final answer you got 4749. Okay, so that's the answer in the base 10. So any question up to that point?
No, doctor.
Okay. All right, convert to binary first and then convert to hex. Okay. You can also do the conversion, all right, from base 10 to hex. Okay, base 10 to hex. So before this, a base 16 to, okay, for this is hex decimal. Okay, now decimal to hex. Okay, so decimal to hex. So you need to, okay, you need to expand this. All right, so you need to expand that. So it's like a method before this for you to convert from um, decimal to the binary as well. Okay, for the set decimal to the binary as well. So this one you need to guess. Okay, 45 is between what number of the base 2? Right? It's between 32 and 64, right? As I said, you need to take the smaller number. Okay, you take 32. So because 45 is between 64 and 32. Okay, so you need to take the minimum one. Okay, so you need to get this in terms of hex, in terms of binary. Okay, so you list that. Okay, 32, 16, 8, 4, 2, 1. Okay, and then to get 45, okay, first you take 32. All right. If you 32, you add with 16. Is it exceed 45? Yes, it's exceed. So you cannot add 16. So 32, you add with 8. Is okay? Yes, it is okay. It is only 40. So less than 45. Now, you add 4. Okay, is it okay? Yes, it's okay because it is 44. You add 2. Not okay because it's already 46. So you just need to add only one more. So just add 1. Okay, so it will be 45. Right? Okay, so from here, so you already have in terms of binary. So your binary is, okay, so you look here. Okay, you look here. So your binary is 1 0 1 1 0 1 base 2. But as I said, you need to remember that in order to convert binary to hex, you need to group 4 bits. Okay, you need to group 4 bits. So you take from the least significant bit. Okay, this is the first group, and then this is another group. But as you can see, it is missing in the front, right? So if it is missing 2 terms in front, you just add 0 and 0. Okay, now it looks a 4 and 4. Okay. So what it is in terms of 16? So this is 2 to 0 and then 2 to 1. So it is 2. Okay. And this one 2 to 0, 2 to 1, 2 to 2, 2 to 3. Okay. 8 plus 4, 12, and 13. So 13 is equivalent to what? So you have already 9, right? 9. 10 is A. 11 is B. Okay. 12 is C. And then 13 is D. Okay. So if you forgot, you can write back the table as I shown here. Okay. 13 is D. All right. So it is 2D hex, or you can write 2D16. It doesn't matter whether you write 2D hex or 2D16. Okay, so you look at another example. So convert 6 to 9 to hex. So as usual, so you need to check. So what is the base 2 number that is between 6 to between that 6 to 9? I mean, so it is between 512, right? 512 and 1024. So between 1024 to 512. Okay, so you need to take the smaller term. Okay, between 1024 and 512. All right, so you need to take smaller term. Okay, and then you list out all of the base 2 number until 220. 12226, 128 until 1. All right, and then so first you take 512, and then how many left? Right? Let's say 629 minus 512. So you still have 117 to be summed up. Okay, so this will be 0 because it's more than 117. This is also will be 0. And then you add 64. So 64 minus that 117. So you still left with 53. Okay, 52 is okay? Yes, it is okay. So 32. So 53 minus 32. Okay, you got 21. So 21, it is okay for 16? Yes, it is okay. So you minus 16. Okay, you left 5. So it is 8 not okay because it's more than 5. Okay, 4 is okay? Yes. 2 is okay? No, because it's more than 1. And then you have 1. So you take this one, 1, and 1, and 1, 1, and 1. So you sum all of that. Sorry. Okay, my mistake. All right, so you take all of this number, all right, for the binary. So because you convert to binary, you take all of this. So you need to group each 4. Okay, that one, and then that one. Okay, because this is only 2 terms, so you add 0 and 0 at the front. Okay, so what it is? So this is 2, 0 to 1. So it's 2, and 2 to 1 to 4. Okay, so 1 to 4 is 7. All right, so this is 1, 0, 1, 2, 4, 5. So it is 5. Okay, 275 hex. Okay, so you have bigger number. All right, so bigger number is between. All right, so 2 to the 5. Okay, 2 to the 8. 2 to the 11. Okay, so 2 to the 10 is 1024, and 2 to the 11 is 2048, because this number is between 2048 and 1024. So that's why we take this number. Okay, 1024. So it is similar procedure like that. So you sum up all of that until you get this binary. Okay, this binary is similar to the 1714. Okay, so you do multiplication of this, so you get that 1714. So you group 4 and 4. So this one got 3 and then 1 missing. So you add 1 0 there. So it should be, all right, this is 2, 2, this is 1, 2, 4. Okay, 6. All right, this is 6, 8, okay, 8 to 10, 11. So 11 is, okay, 9, A is 10, 11 is B. So it is B. And then this one is 2. All right, so 6B2X. Okay, so that's how you do the conversion. Okay. All right, this is for more than 16. This is for more than 16. Okay. Right, so there is more than 16. So you have, after that, in the hex, because the maximum, all right, because the maximum if is between 0 and F, so it's F. So after you finish F, so you start with 1 in the front. Okay, start 1 in the front and then put back. Okay, put back all of this number. So all of that number. Okay, you have 1 in the front and put back all of that number. Okay, you are clear? So you have now, we have 16 and 32 numbers, all right? So it's from 0 to 31. So you have 32 bits now. All right. Okay, so that's it for today. Okay, for Thursday, we will learn on how to do addition. Okay, addition between two two binary numbers, all right, or even two decimal numbers or two hex numbers. Okay, any questions so far? So I stop here for today. Okay. All right, so everyone is clear with what was learned today. So I hope you can catch all of that. Okay. So if you have any further question, you can ask me. I made the recording, so it should be available later today. And I will share also the lecture notes.
How about the attendance?
Attendance. Now is the time for attendance. So let's turn on the camera for all of you. I'm going to snap the picture. Okay. I'm giving you 20 seconds. All right. So I'm taking the attendance now.
Yeah. Okay.
All right. So let's count. Okay, from 10. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Cheers. Okay. All right. Okay, so that's it for today. So I see you again on Thursday. All right. Any question? You can let me know. Okay, so bye-bye for now. Okay, see you on Thursday. Assalamualaikum.
Thank you, Doctor.
Thank you, doctor.
Terima kasih doktor.
Thank you, Doktor.
Thank you, doctor.
See you again, Doktor.
Thank you,
Okay, see
Doctor.
you. Bye-bye.
Thank you, Doctor.
Thank you doktor.
Thank you, Doctor.
Thank you, Arif.
Thank you, Amor.
Thank you Arif. Thank you Cik Izan.
Thank you, Arif. Recording.